Welcome, everyone. Today, we are not just exploring a technology, we are solving a mystery. We are diving into the world of generative modeling, specifically denoising diffusion models, through the lens of a forensic investigation. The title, Emergence, captures the essence of what these models achieve, creating order from noise. For decades, generative artificial intelligence struggled with the fundamental problem of creation. How do you generate a photorealistic image, a complex musical piece, or a new piece of data structure out of thin air? The methods were often chaotic and unpredictable. Denoising diffusion changes this paradigm entirely. It frames the act of generation as a meticulous, forensic reconstruction of reality. Imagine the world has been shattered into pure static, reduced to the brink of chaos. This new method provides the tools to reverse that destruction, step by step, deducing the original reality from the ruins. This is the principles of denoising diffusion, framed as a forensic reconstruction of reality from the brink of chaos. It is a new, powerful, and surprisingly logical approach to generative modeling, and over the next few minutes, we will unpack how this detective work is accomplished. To understand the solution, we must first understand the problem, a signal lost. We begin with a perfect reality, stage 1, perfect order. Here, we see a complex mechanism, like a meticulously engineered watch, representing a structure of pure, pristine information. This is the truth we are seeking to recover. The crime begins when chaos is introduced. In stage 2, introducing noise, a small amount of static or Gaussian noise is added. This process continues systematically, increasing the corruption over time. In stage 3, signal degradation, the features become blurred. In stage 4, structure erosion, the defining details start to disappear, buried under increasing layers of chaos. Finally, we reach stage 5, total chaos. The original signal is completely erased, leaving nothing but pure, undifferentiated random static or noise. The image is gone. The fundamental question for any generative model is posed here. How do you rebuild a reality that has been lost entirely to chaos? The genius of diffusion models lies in the fact that they turn this question on its head. Instead of trying to recreate the original image from scratch, they focus on understanding and reversing the destruction process itself. Historically, when creating new data, older methods of generative modeling, such as generative adversarial networks or early variational autoencoders, attempted to generate the signal from a blank slate. This was often an uncontrolled, difficult, and sometimes unstable process, lacking true predictability. But now, a new detective arrives, denoising diffusion models. These models operate under a completely different discipline, reconstruction. Think of them not as artists painting a new picture, but as forensic investigators meticulously reversing a crime scene. Their function is deduction. They are not trying to guess what the original signal was, they are trying to deduce it by meticulously studying how it was destroyed. Because they know the exact rules of the destructive process, the forward process we just saw, they can learn to reverse it perfectly. This disciplined, stepwise reversal gives them unparalleled stability, fidelity, and control over the generation process. Diffusion models offer a powerful and controllable way to generate high-fidelity data. This entire presentation is, in essence, the story of how this new breed of digital detective operates, learning to walk backward in time from chaos back to coherence. Our first lesson in digital forensics focuses on the crime itself. Forensics 101, the forward process. The key takeaway here is control. The forward process is a controlled deconstruction, a fixed Markov chain that adds Gaussian noise over a large number of time steps. Denoted by T, we start with the clean image x0. At each small step, T, a predefined, small amount of Gaussian noise is added. This results in image x1, then x2, and so on until we reach xd, which is pure static. This process is mathematically defined by the conditional probability Q of x1 given x0. The crucial insight here is that this is not random, unpredictable chaos. It is a perfectly predictable, mathematically defined process. The variance of the image is kept constant throughout. We know exactly how much noise is added at every single step. Because we, the detective, have this complete blueprint of destruction, we know exactly how the signal was lost. This knowledge is our most valuable asset because it provides us with the necessary constraints and structure to guarantee a successful recovery later on, forming the foundation of the diffusion model's operation. The way noise is added is so crucial it is considered the signature of chaos, or the diffusion schedule. This schedule, often denoted as beta t, determines the specific rate at which noise is introduced over the time steps t. A linear schedule adds noise steadily throughout the t steps. However, research found that a cosine schedule is often more effective. Why? Notice how the cosine curve starts very shallow, meaning it adds noise much more gradually at the initial stage. This gradual initial corruption preserves signal integrity for longer, which is critical for training stability and final image quality. This choice is a core design decision in any diffusion implementation. But even with a perfect schedule, imagine having to simulate thousands of steps every time you want to check a specific point in the corruption. That would be computationally impossible. This brings us to the master key, the reparameterization trick. This mathematical insight allows the model to instantly jump directly from the clean image x0 to any corrupted image xt in a single, non-sequential step, without needing to replay the entire crime. The formula shown combines the original signal x0, weighted by the square root of alpha t bar, with pure noise epsilon weighted by the remaining variance. This genius trick is our detective's ability to instantly access any moment of the deconstruction for analysis, providing the efficiency required for millions of training iterations. With the forward process mapped out, we can now discuss the reversal, predicting the past. This is the detective's core task. We start from the state of total chaos, xd, and must walk backward, step by step, back to x0. The objective is to train a neural network, denoted as epsilon theta, that can completely undo the noising process. Given any corrupted image xd at a specific time t, the model's sole, precise job is not to predict the original image directly, but to predict the exact noise, epsilon, that was added to create that corruption. It predicts the agent of chaos itself. Once the model predicts this noise, epsilon theta, we simply subtract it from the noisy image xd to get a slightly cleaner image xd1. By repeatedly performing this process, predicting and subtracting this small piece of noise over hundreds or thousands of steps, the detective walks backward in time, performing a meticulous reconstruction from pure static to a coherent, detailed image. This focus on predicting noise rather than the signal itself is the fundamental breakthrough in denoising diffusion models. What kind of neural network is capable of such meticulous deduction? Inside the detective's mind, we find the UNet. This architecture is perfectly suited for image-to-image tasks like denoising. It takes the shape of a U divided into two primary paths. First, the downsampling path, or the evidence-gathering stage. Here, the network compresses the noisy image, xd, analyzing the scene at multiple scales. This allows it to capture both the broad context of the image and the very fine pixel-level details. This compression process forces the model to focus on the essential features. Second, we have the upsampling path, or reconstruction. This path rebuilds the signal, using the gathered evidence from the downsampling path to meticulously reconstruct the image. Crucially, the model receives two inputs: the noisy image xd and also the time step t itself, which is the level of noise variance. This time step is encoded via a sophisticated sinusoidal embedding. This ensures the model has a clear sense of when, in the crime, or which stage of corruption, it is currently operating. Knowing the level of corruption is essential for predicting the correct amount of noise to subtract, making the UNet highly effective. While the UNet structure seems familiar to architectures like variational autoencoders, it has one critical advantage that makes it perfect for denoising high-fidelity images: the critical clue of skip connections. In a traditional sequential autoencoder, information must travel all the way through the network's central, most compressed bottleneck. High-resolution details often get lost or forgotten during this intense compression. The skip connections act as informational highways, bypassing the bottleneck entirely. These connections allow raw, high-resolution details from the early evidence-gathering stages to be directly transferred and accessed during the final reconstruction stage. This ensures that fine details, which are often the most fragile elements of an image, are preserved through the entire decoding process. For our detective, the skip connection is the network's perfect memory. It prevents the model from forgetting crucial clues, ensuring that the sharp edges and fine textures of the final generated image are accurate and high fidelity. This design feature is fundamental to why diffusion models produce such crisp and realistic output compared to their predecessors. Training the detective requires honing the instinct, the training regimen. This process is repeated millions of times, essentially solving millions of microcrimes until the unit is highly accurate at its prediction task. Step 1. We start with a clean, uncorrupted image x0. Step 2. We pick a random time step t and corrupt x0 to xd using the defined forward process. Step 3. We feed this corrupted image xd and the time step t into our unit. Step 4. The unit makes its prediction epsilon theta the predicted noise. Step 5. We calculate the loss. This is where the model is told how wrong it was, measuring the difference between the predicted noise epsilon theta and the true noise epsilon that was initially added. This calculation, often mean squared error, drives the learning. Step 6. Based on the error, we update network weights. Repeat. This constant feedback loop allows the model to become incredibly precise at predicting noise across all stages of corruption. Finally, we maintain a separate set of weights called the exponential moving average, or EMA network. This EMA network is less susceptible to short-term training fluctuations and provides a smoother, more generalized representation of the model's knowledge. It is the grizzled veteran's gut feeling, used for the final, high-stakes generation process because of its proven stability and robustness. With training complete, the detective is ready to work on an unsolved mystery. This phase is called cracking the case, the sampling process. We begin at step 0 with a random configuration of static, pure noise. XD this is the blank canvas for generation. The model then applies its learned reversal process. At each step, it predicts the total noise in the image using the unit. It uses that noise estimate to estimate what the original, clean image, x0, would look like. Then, it uses that pristine estimate to take a calculated, deterministic step backward in time to the slightly cleaner image, xd1. We specifically use a variant called the Denoising Diffusion Implicit Model, or DDIM, which makes the sampling process entirely deterministic. The sequence shown demonstrates this progression. From pure noise, we move to step 5, then step 10, gaining clarity and structure, until we reach step 20, where order is restored. The crucial aspect of DDIM is determinism. Unlike probabilistic models, the same starting noise will always yield the exact same stunning, high-fidelity conclusion. This is pure logic at work, not luck, enabling reproducible and high-quality generation. After all the meticulous forensic work, what is the ultimate result? It is not merely reconstruction of a known image, it is creation. The model has learned the underlying structural rules, the grammar of watch design, not just memorizing specific pictures. From a universe of complete random noise, the model imposes order, generating novel realities that are entirely consistent with the complex patterns it has learned. Look at the variety here, from polished dress watches to rugged chronographs and complex tourbillons. None of these exact images existed in the training data, yet the model produces them with flawless detail and coherence. The text in the middle summarizes this well. The result is not just reconstruction, but creation. From a universe of random noise, the model imposes order, generating novel realities consistent with the patterns it has learned. The diffusion model's ability to predict and subtract noise is essentially equivalent to mastering the underlying data manifold. It understands the design space so intimately that it can locate previously unseen, high-quality data points within it. This demonstrates the profound power of having a model that truly understands the transition between order and chaos. One of the greatest advantages of diffusion models is the profound control they offer. Mastering the craft allows us to manipulate the generation process to achieve specific results. First, fidelity is tied directly to the rigor of the investigation. As we see in the top row, increasing the number of diffusion steps, that is, making the detective take a more meticulous, smaller steps backward in time, yields a higher fidelity result. Going from 5 steps to 50 steps produces a much sharper, more accurate image. This direct trade-off between quality and computational time provides flexibility. Second, diffusion models allow for seamless latent space interpolation, which means navigating the design space itself. The latent space is the mathematical area where the noise lives. By starting with two different noise samples that generate two distinct watches and smoothly transitioning the initial noise from one state to the other, the model generates smooth, coherent transitions between generated realities. This is shown in the bottom film strip. This is not surface-level mimicry. This demonstrates that the model has a deep, structural understanding of the features and forms that define the data, enabling it to smoothly morph one complex object into another, proving its mastery over the generative task. Let us summarize the entire process that defines the new law of the land in generative modeling, organized into three major acts shown here visually. Act I, the crime or the forward process. This is where a perfect signal is systematically lost to predictable chaos. This controlled destruction provides the necessary blueprint for the recovery. Act II, the method or reverse process training. A new kind of detective emerges, the UNet. Its training goal is revolutionary. It is trained not to find the lost signal, but to identify the precise signature of the chaos itself, predicting the noise, epsilon, at any given time step. This is done through training the UNet. Act III, the resolution or DDIM sampling. Through a meticulous, step-by-step forensic reconstruction, the model learns to reverse the decay. It restores order from static, and critically, gains the ability to create entirely new, coherent realities at will. This full cycle, from controlled corruption to learned reconstruction, defines the power and stability of denoising diffusion models and their impact on generative AI. Before we conclude, let us consolidate the dossier of key terminology we have discussed today. The forward process, designated as Q, is the fixed Markov chain that gradually adds Gaussian noise to the data according to a variance schedule. Its inverse is the reverse process, P theta, the learned Markov chain parameterized by the UNet that denoises the data by predicting the added noise, epsilon. The reparameterization trick is the crucial mathematical shortcut, allowing us to sample any state xd at any time step t directly from the starting image x0 and the noise epsilon, which is essential for efficient training. The diffusion schedule beta t is the predefined variance of the noise added at each time step. Cosine schedules have been shown to typically outperform simpler linear ones due to better signal preservation. The UNet is the neural network architecture itself, characterized by its downsampling and upsampling paths connected by skip connections, making it ideal for robust image-to-image processing. DDIM, or denoising diffusion implicit models, is the variant that provides deterministic sampling, enabling reproducible generation and facilitating powerful latent space manipulation. Finally, the EMA network is the exponential moving average of the model's weights, used during inference for stable and robust final generation quality. We started this journey with chaos, a reality lost to pure noise. We conclude by recognizing the profound shift that denoising diffusion models represent. They have taught us that generative modeling is not about magic or guessing. It is about precision, control, and forensic deduction. They show us that by understanding the nature of destruction, we gain the ultimate power of creation. The ability to pull forth complex, high-fidelity structures from pure static is a testament to this principle. Whether we are generating photorealistic images, designing new materials, or creating complex synthetic data, the underlying mechanism remains the same: reversing the decay of information. Diffusion models have given the field a new foundation, shifting the paradigm from uncontrolled generation to meticulous reconstruction. This metaphor holds true across all applications of diffusion, from image synthesis to music generation. We are no longer limited by what we can write or paint from scratch. Instead, we have learned to uncover the future that is already latent within the noise itself. The future isn't written, it's denoised. Thank you for joining this exploration.